November 1939, LaGrange, Illinois. Inside Electromotive Corporation's drafting hall, Chief Engineer Richard Dilworth watched his design team finalize blueprints for a locomotive that would attempt something the railroad industry considered fundamentally impossible. Every transportation executive knew the established truth. Diesel engines lacked the power for heavy freight. They couldn't match steam's raw pulling force, couldn't handle America's mountain grades, and certainly couldn't survive the punishment of cross-country operations hauling thousands of tons daily. European railroads had proven this for over a decade. Diesel worked fine for passenger trains and light-switching duties, but serious freight required steam power's massive boilers and driving wheels. Accept this limitation or abandon diesel entirely for mainline service. But Dilworth's team proposed something that contradicted every assumption about locomotive engineering. Build a diesel freight locomotive using 4 separate power units working together, each generating 1,350 horsepower through electrical transmission instead of mechanical drive rods. Design every component for field replacement without specialized tools. Create a cooling system that could function reliably from desert summers to Rocky Mountain winters. The engineering room fell silent as cost estimates arrived. The prototype would consume nearly all of EMD's development budget during America's economic recovery from the Great Depression. Railroad customers weren't requesting diesel freight power. Steam locomotive manufacturers dominated the market with proven designs refined over a century. Choosing this experimental path meant betting the company's future on technology that established railroads actively distrusted. The diesel they were designing would run for decades without major mechanical failure, convincing an entire industry to abandon steam power forever. But first, they needed to survive the demonstration phase. The telegram from Santa Fe Railroad reached EMD headquarters on December 2, 1939. Railroad President Edward Engel had agreed to test the experimental diesel units, but his message carried unmistakable skepticism. Santa Fe operated 3,600 miles of mainline track across some of America's most demanding terrain, from Chicago's flat prairies through New Mexico's desert grades to California's coastal mountains. Their freight operations depended on massive 210-4 steam locomotives that could pull 4,000-ton trains up 108% grades through Raton Pass. Engel's engineering staff had calculated brutal mathematics. Steam locomotives generate drawbar pull through direct mechanical connection between pistons and driving wheels. A modern 210-4 could produce 93,000 pounds of tractive effort at starting, enough to move entire freight from standstill on steep grades. Diesel-electric transmission seemed inherently inferior, converting fuel energy to mechanical rotation, then to electrical generation, then back to mechanical traction through wheel motors. Each conversion lost efficiency that steam's direct drive avoided. The technical objections went deeper than simple power calculations. Diesel engines required precise fuel injection, electrical generation equipment that could fail catastrophically, and traction motors exposed to track debris and weather extremes. Steam locomotives broke down regularly, but railroad mechanics understood their relatively simple systems. Diesel technology meant training entirely new maintenance crews in electrical systems, generator theory, and complex fuel management that traditional railroad workers had never encountered. Harold Johnson had worked as Santa Fe's master mechanic at the Argentine Yard in Kansas City for 23 years, supervising repairs on hundreds of steam locomotives. He understood every component of a Mikado 282, could diagnose bearing problems by sound alone, and kept detailed records of maintenance patterns that predicted when boilers needed inspection or driving wheels required truing. His mechanical intuition came from decades of hands-on experience with technology unchanged in fundamental principles since the 1800s. When Santa Fe's management announced plans to test EMD's experimental diesel in early 1940, Johnson gathered his foremen to review the technical specifications that accompanied the railroad's announcement. The documents described 4 separate diesel engines, each connected to electrical generators feeding traction motors on individual axles. The complexity seemed overwhelming compared to steam's straightforward design. Steam locomotives required regular maintenance, certainly. Boiler washouts every 30 days to remove mineral deposits, driving rod inspections after each heavy run to check for stress cracks, lubrication of dozens of moving parts that operated at temperatures exceeding 400 degrees Fahrenheit. but these were known problems with established solutions that any competent mechanic could handle using standard tools and readily available parts. Diesel maintenance manuals described electrical systems that required specialized testing equipment, fuel injectors calibrated to tolerances measured in thousandths of an inch, and cooling systems using ethylene glycol instead of simple water. The diesel engine itself, EMD's new 567 design, used 16 cylinders arranged in a V configuration, each with its own fuel injection pump, exhaust valve system, and lubrication requirements. A single component failure could disable the entire power unit unless mechanics could diagnose electrical problems they'd never been trained to handle. Railroad executives shared mechanics' skepticism for financial reasons that seemed equally compelling. Baldwin Locomotive Works had supplied American railroads with steam power since 1831, refining designs through generations of incremental improvements. Steam locomotives represented understood technology with established manufacturing capacity, proven reliability data, and comprehensive parts supply networks spanning the continent. Switching to diesel meant abandoning this infrastructure for experimental technology from a manufacturer with limited freight locomotive experience. The investment implications troubled railroad financial officers reviewing EMD's proposals. A modern steam locomotive cost approximately $200,000 in 1940, representing substantial capital investment, but backed by decades of operational data that permitted accurate cost forecasting. EMD's diesel units would cost significantly more per locomotive, with maintenance expenses that remained purely theoretical since no diesel had operated long enough under freight service conditions to establish reliable maintenance schedules or parts replacement intervals. Insurance companies added their concerns, questioning whether diesel locomotives qualified for standard coverage rates. Steam locomotive fires were common enough that railroads maintained dedicated firefighting equipment at major terminals. But diesel fuel fires presented different hazards, potentially more severe since burning diesel oil was harder to extinguish than coal fires. Without established safety records, insurers couldn't accurately price policies for diesel operations, creating additional financial uncertainty. By spring 1940, industry consensus had solidified around a cautious position. Diesel might work for passenger trains and switching operations, but freight service demanded proven steam technology. EMD's experimental units would likely demonstrate diesel's inherent limitations rather than any revolutionary capabilities. Richard Dilworth's career had prepared him for exactly this kind of skepticism. He'd spent the 1920s developing diesel engines for submarines, where reliability wasn't optional, and mechanical failure meant catastrophic consequences far beyond railroad operations. Submarine diesels ran continuously for weeks underwater, operating in confined spaces where overheating could kill crews and maintenance required completing repairs with limited tools in cramped engine rooms. Those submarine design principles shaped every aspect of the FT locomotive. The 567 engine designation indicated each cylinder's displacement in cubic inches, reflecting Dilworth's obsession with modular standardization. Every cylinder used identical pistons, valves, and fuel injectors that could be swapped between positions without custom fitting. The V16 configuration balanced power output against physical dimensions that could fit within railroad loading clearances while allowing mechanics to access any cylinder for maintenance without removing other components. The fuel injection system represented breakthrough engineering that addressed railroad executives' concerns about diesel reliability. Each cylinder received fuel through individual injection pumps mechanically driven by the engine's camshaft, eliminating complex hydraulic systems that could fail catastrophically. If one injector malfunctioned, its cylinder simply stopped contributing power while the other 15 continued operating. The engine would lose savies of total output but remain functional until mechanics could replace the failed component during scheduled maintenance. Cooling system design revealed Dilworth's understanding of American railroad geography. Steam locomotives consume thousands of gallons of water daily, requiring frequent stops at water towers strategically positioned along mainline routes. Diesel engines needed continuous cooling, but EMD's engineers designed a closed-loop system using ethylene glycol that could operate indefinitely between maintenance intervals. Radiators positioned along the locomotive's roof used forced air cooling that functioned effectively in temperatures ranging from 40 degrees in Montana winters to 120 degrees in Arizona summers. The electrical transmission system addressed the fundamental power delivery challenge that made railroad executives doubt diesel's freight capability. Steam locomotives transmitted power through rigid drive rods connecting pistons directly to driving wheels. This mechanical linkage provided maximum pulling force at low speeds but created severe mechanical stress that frequently broke rods during hard starts or emergency braking. Diesel-electric transmission eliminated these mechanical components entirely, using generators to convert engine rotation into electrical current that powered traction motors on each axle. This electrical approach offered advantages that steam couldn't match. Traction motors delivered consistent pulling force across all speed ranges from starting effort through maximum velocity. Electronic controls prevented wheel slip automatically, whereas steam engineers had to modulate throttle manually during difficult starts on grades. Most importantly, electrical transmission meant no reciprocating masses to create dynamic stress that broke mechanical components under heavy loads. EMD's modular design philosophy extended throughout the entire locomotive. Rather than building one massive 5,400 horsepower engine, they created 4 separate 1,350 horsepower units that could operate together or independently. If one unit failed during operation, the train continued using remaining power. Maintenance crews could replace an entire power unit in hours, rather than spending days repairing complex internal components while the locomotive sat idle, blocking valuable terminal space. The first FT demonstrator units rolled off EMD's assembly line in November 1939, designated FT-103 through FT-106. 4 locomotive units painted in striking two-tone gray with yellow trim that announced their experimental status to every railroad worker who saw them pass. Together, they stretched 202 feet and weighed 912,000 pounds, making them longer than any steam locomotive but surprisingly lighter given their combined horsepower rating. Santa Fe Railroad agreed to host the first demonstration, committing to a comprehensive test program that would subject these experimental diesels to every operational challenge their system could provide. The test schedule began modestly with light freight runs between Argentine Yard in Kansas City and Shopton, Iowa, allowing EMD's engineers to verify systems under real railroad conditions before attempting more demanding operations. William White supervised those initial test runs, monitoring engine temperatures, generator outputs, and traction motor performance, while crews learned to operate locomotives that bore little resemblance to familiar steam power. The FT units accelerated smoothly, without the jerking motion typical of steam locomotives starting heavy trains. They maintained consistent speed-up grades without the dramatic exhaust sounds that announced steam engines working hard. Most remarkably, they required almost no attention from crews during runs, operating hour after hour with only occasional monitoring of instrument gauges. By January 1940, Santa Fe's confidence had grown enough to attempt serious testing through Raton Pass, the notorious mountain crossing that defined whether locomotives could handle genuine freight operations. The eastbound climb from Trinidad, Colorado to the 7,588-foot summit stretched 35 miles, with grades reaching 3.5%, among the steepest sustained grades in American railroading. Steam locomotives typically required double-heading, using 2 engines together to move standard freight over this obstacle. The FT units departed Trinidad on January 15th, hauling 66 loaded freight cars weighing 3,254 tons, a tonnage that would normally require 2 modern 210-4 steam locomotives working together at maximum capacity. White monitored engine temperatures nervously as the diesels began climbing, watching coolant gauges and noting exhaust temperatures that measured internal combustion efficiency. The diesels climbed steadily, maintaining 20 miles per hour throughout the steepest sections without any signs of overheating or power loss. White's logs recorded consistent performance that seemed almost mundane, temperatures stable, fuel consumption predictable, traction motors drawing appropriate current. The routine reliability was itself remarkable because it indicated nothing dramatic was happening internally. The engine simply worked, converting diesel fuel to mechanical power with an efficiency that thermodynamics predicted but railroad experience hadn't previously achieved in freight service. At the summit, Santa Fe's observers calculated performance data that would circulate through railroad industry offices within days. The FT units had climbed Raton Pass in 2 hours and 16 minutes while consuming 278 gallons of diesel fuel. Two steam locomotives would have required approximately 4 hours with multiple stops to add water and rebuild steam pressure. The comparison demolished assumptions about diesel's inadequacy for heavy freight operations, but the demonstration was just beginning. Santa Fe authorized extending the test program indefinitely, using the FT units for regular freight service while documenting every operational detail. Through spring and summer 1940, the FT units accumulated mileage that transformed railroad industry opinions about diesel reliability. Santa Fe crews operated them continuously on freight runs between Chicago and Los Angeles, covering 2,227 miles each direction through dramatically varying terrain and climate conditions. What emerged from this extended testing wasn't dramatic failures or spectacular breakdowns, but rather the absence of problems that plagued steam operations. Harold Johnson began documenting maintenance requirements that contradicted everything his experience with steam locomotives had taught him. Steam engines required daily inspections before entering service, checking boiler water levels, examining drive rod connections, lubricating dozens of high-temperature bearing points. The FT units required crew members to verify fuel levels, check engine oil, and confirm electrical systems showed proper voltage. These inspections took minutes rather than hours. More remarkably, the diesels operated day after day without the constant minor repairs that consumed steam locomotive maintenance budgets. Steam engines leaked constantly from cylinder packing glands, valve stems, and countless threaded joints exposed to extreme pressure and temperature. Every leak meant lost efficiency and potential component damage requiring immediate attention. The FT's closed systems eliminated these chronic problems, operating through entire transcontinental runs without adding fluids or addressing developing issues. The modular design philosophy proved its value during the few problems that did occur. In April, one power unit developed a fuel injector leak that reduced its output. The crew simply isolated that unit and continued operating on 3 remaining power units, maintaining schedule with minimal performance reduction. At the next major terminal, a maintenance crew replaced the failed injector pump in 90 minutes using standard tools and a spare part carried in the locomotive's equipment locker. A comparable steam locomotive repair would have required removing the engine from service for days while specialized craftsmen fabricated replacement components. Cooling system performance exceeded design specifications across temperature extremes that challenged both steam and diesel technology. During July operations through Arizona and Southern California, outside temperatures reached 118 degrees in desert sections where steam locomotives struggled to maintain adequate water supply. The FT's closed-loop cooling system maintained engine temperatures within normal operating ranges using fans that increased airflow automatically as heat loads rose. The system required no external water supply beyond periodic coolant replacement at maintenance intervals measured in thousands of miles. Winter testing proved equally impressive when temperatures dropped below 20 degrees across Montana during December 1940 operations. Steam locomotives required keeping fires burning overnight to prevent boiler water from freezing, consuming fuel and labor even while stationary. The FT units shut down completely when not needed, then restarted reliably using electrical heating systems that warmed fuel and lubrication oil before engine cranking. The diesels were ready for service within 30 minutes of starting procedures, compared to hours needed to raise steam pressure from cold boilers. By early 1941, the FT demonstrators had accumulated over 83,000 miles in regular freight service without a single failure requiring towing by another locomotive. This reliability record exceeded anything achieved by newly built steam locomotives, which typically experienced break-in problems during initial service requiring extended repairs as components seated properly. The diesels simply worked, mile after mile, establishing operational reliability that railroad executives had considered impossible. Financial data from Santa Fe's extended FT testing reached railroad executive offices across America during early 1941, containing numbers that challenged fundamental assumptions about locomotive economics. The diesels consumed 7 gallons of fuel per 100 miles, hauling typical 3,000-ton freight. At prevailing diesel fuel prices of 7 cents per gallon, fuel cost totaled $10.29 per 100 miles. Comparable steam operations consumed approximately 5 tons of coal at $4.50 per ton, plus 8,000 gallons of water requiring treatment and handling infrastructure. Total operating costs per 100 miles for steam exceeded $35 when factoring in water system maintenance and fuel handling labor. The maintenance cost differential proved even more dramatic. Santa Fe's accounting department calculated that FT units required scheduled maintenance every 92 days based on actual operational data. These maintenance intervals involved oil changes, air filter replacement, and systematic inspections that rarely revealed problems requiring component replacement. Steam locomotives required monthly boiler washouts, bi-weekly lubrication services, and constant attention to wearing components like valve gear, drive rods, and boiler tube systems. Annual maintenance costs per locomotive averaged $47,000 for steam power compared to $18,000 for diesel operations. Railroad mechanical departments began requesting EMD demonstrations on their own systems, eager to verify whether Santa Fe's experience could be replicated under their specific operating conditions. By mid-1941, the FT demonstrator units were embarked on an 11-month, 35,000-mile tour visiting 20 different railroads from Pennsylvania to California. Each railroad designed test programs addressing their particular operational concerns. Heavy coal drags in Appalachia, high-speed freight operations across flat Midwest prairies, mountain operations through the Rockies and Cascades. Great Northern Railway tested the FT units through Montana's 2.2% grade over Marias Pass during February 1941, comparing performance against their massive articulated steam locomotives specifically designed for mountain service. The diesels hauled 3D 100-ton trains over the pass while consuming less fuel and requiring no helper locomotives on the steepest sections. More impressively, they maintained precise speed control descending the eastern slope where dynamic braking systems dissipated momentum electrically instead of relying solely on air brakes that could overheat during prolonged mountain descents. Pennsylvania Railroad conducted dynamometer testing measuring precise drawbar pull under controlled conditions. Their engineers confirmed that FT units developed 56,000 pounds continuous tractive effort at 10 miles per hour, matching or exceeding steam locomotives of comparable weight. More significantly, the diesels maintained this pulling power consistently regardless of grade or weather conditions, whereas steam locomotive performance varied with coal, quality, water chemistry, and operator skill in managing steam pressure. Southern Pacific tested the diesels through California's Central Valley during summer heat that challenged steam operations with chronic water supply problems. The FT units operated through 110-degree temperatures while hauling time-sensitive perishable freight that demanded schedule reliability. Steam locomotives on these routes frequently required stops to add water at facilities positioned every 30 to 40 miles. The diesels ran entire 300-mile segments between major terminals without servicing stops, providing schedule advantages that translated directly to improved customer service. By December 1941, EMD had received firm orders for 555 FT locomotives from multiple railroads convinced by demonstration tour results that diesel freight power had proven itself under every significant operational challenge.